Welcome back to the lecture series on data structures. In this lecture, we will look into the aspects of graph theory, how graphs can be used to represent the connectivity among the data objects, and how do we store the data. Whenever there is a collection of objects and there is a relationship among the objects in the group, among themselves in a particular manner, we can represent that relationship mathematically in the form of a graph. Typically, a graph can be considered as a pair set of vertices and edges, where vertices will represent the objects and edges will represent some kind of relationship among the objects. The nature of the relationship may be different in different scenarios, but the abstract view of the relationship among the objects can be represented in terms of edges. Because of the versatility and ease of implementation, graphs are considered as a very useful tool to represent the relationship among entities or objects. There are various types of graphs are there. In this lecture, we look into the jargon of the graph theory, which is required for the construction of the data structure with respect to the graph. And we look into the aspects of storing data and representation of the graph for an algorithm approach. So to start with, if there is only one vertex is there, that is called a single vertex, which is called a trivial graph. And if each pair of vertices are adjacent with respect to each other, that means adjacency means there is an edge between the vertices. Then if such a graph is called complete graph. And if between any pair of vertices at most one edge is there, then it is called a simple graph. And if there are more than one edges are there, then it is called a multi-graph. And if there are no edges present between any pair of vertices, only vertices are present, such a graph is called null graph. Similarly, if a graph contains equal number of edges incident on each vertex, then it is called a regular graph. And if every edge of the graph is labeled with some weight, some number, then it is called a weighted graph. Or if the edges are labeled with some text, that is called a labeled graph. These are all the preliminary types of graphs. The graph is said to be connected if we can reach from any vertex to any vertex through a path. A path means a collection of sequential edges starting from one vertex through a connectivity of vertices through reaching another vertex. And the graph is said to be disconnected if graph consists of more than one subgraph which are not connected. That means there is no path from one subgraph to another subgraph. We cannot reach from one subgraph to another subgraph. So it is called a disconnected graph. And if there is a cycle, that means if we start at a vertex and tracing through the edges, if we are able to come back to that vertex, then it is an indication of presence of a cycle. So then if there is at least one cycle, then it's called a graph is said to consider having cycles. And directed graph is also another special case where the edges may have a direction, the starting vertex and ending vertex. So it will be denoted by arrows. And the subgraph is a part of the graph which itself can be considered as a graph, is called a subgraph. The visual representation of graphs is very easy to comprehend, but when it comes to a program, how to represent the data of the nature of the graph to a program. For this, there are two facilities are there for us. One is we can represent them in the form of a matrix, which is called adjacency matrix. Adjacency matrix means we'll consider a matrix with rows as vertices, and again columns are also vertices. Whenever there is an edge between a pair of vertices, we'll place 1 there. If there is no edge between a pair of vertices, we put 0. Such a matrix is called adjacency matrix. And for undirected graph, if the edges are not directed, then the graph is a symmetric graph, as there is no distinction between A to B, edges A to B and B to A. Now, when it comes to a directed graph, the edge will have a direction from one vertex to the other vertex. In this case, the corresponding matrix will not be symmetric, but similar matrix can be represented in case of directed graphs also. And another representation of graphs is in the form of adjacency list. That is, a linked list of linked lists can be represented here. For each vertex, from each vertex, we can reach a collection of other set of vertices. Now, if I start with a vertex in this graph, with vertex 1, I can reach vertex 2 and vertex 3 from 1. So, for the first node, in the first node, I'll take the link to node with the vertex 2 and another node with link to 3. So from 1 I can reach to the vertices 2, 3. Similarly, from 2 I can reach 1. Only one vertex I can reach. From 2 I can reach 1. From 3 I can reach only 2. From 4 I can reach 3, 5. From 5 I can reach 2, 1. So this is how we can represent the quality, the presentation of the graph in terms of linked list of linked lists, or this can also be represented in the form of array of linked lists. In this case, in the array we store the memory addresses of the next nodes. Two more representations are there in terms of incidence matrix and circuit matrix. In case of incidence matrix, the set of vertices will be taken as rows and set of edges will be taken as columns. And we'll put 1 if a vertex is incident with respect to an edge, we'll put 1 there. For example, if I take vertex A, it is incident with 2 edges, 1, 2 are incident on A. So for the respective places, we'll keep 1. Similarly, for B, 1, 3, 4 are the locations or the edges which are incident on B. So we put 1 in the respective places, for all the remaining places 0. This is how we can represent a matrix. Which vertex is incident with respect to which edge. That is called incidence matrix. Similarly, circuit matrix can also be represented with respect to the cycles present. So in this case, 2 cycles are there, and we can represent them in the form of 1, 3, 2, and another cycle is 3, 4, 5, 6. So we can have 2 cycles. Cycle 1 will have 3 edges, 1, 2, 3, and cycle 2 will have 3, 4, 5. 3, 4, 5, 6. Of course, we can also have another cycle here, 1, 2, 5, 4, 6. This is also another cycle may be taken here. So we can have circuit matrix. When it comes to the real-time applications, social media network is a very good example of representation of with graphs. And computer networks, the internet connectivity and devices connected through internet or the globe or a region can be represented in the form of a graph. Not only that, Google Maps is also one of the best examples where different locations are connected in the form of a graph. So we can run applications or algorithms to process the information that is available in terms of graphs. Thank you for watching. If you like the video, you can share it with your friends so that majority of the students can be benefited.